Okay. We have already looked at the capacitor as a lovely way of setting up a constant electric field. And again, this is an artistic representation because this separation D or either way we want to write that, I could also say, write this as D squared has to be way, way less than the cross-sectional area of one of the plates, because if I'm close to the edge of the electric field, there's going to be fringing effects and there's going to be a problem. And we set this up as wonderfully being able to establish a constant electric field. But it turns out they have cool properties in circuitry as well. Because one of the things that we've done is we've looked at this and said, oh, okay, well, if I'm looking at, say, the change in electric potential over this gap, well, I could write that, I would have to start that as negative the integral over the path of E dot dl, but the electric field is constant. So this comes out of the integral. If I'm just looking straight across the gap, then that becomes the difference in length of the side d. So this, delta V is equal to negative. If I'm going with the electric field, the electric potential is dropping. You know, I'm rolling downhill, as it were. The electric field times d. So, we also know, okay, so this we found out from the material in this chapter. We also know before, and this is one of the reasons why I had to talk about chapter 27, even though you're not being tested on chapter 27, is that the electric field of a plane is equal to the surface charge density of the plane divided by 2 epsilon naught, where epsilon naught is a characteristic of, or epsilon is a characteristic of space in that region. Epsilon naught is the characteristic, the permittivity of free space. Well, the permittivity of a vacuum, the permittivity of air is happily very, very close. So if I've got two planes, you know, with a positive electric field on one plate and a negative electric field on the other, then the electric field is 0 outside the gap between the two capacitor plates, and twice the electric field of the plane. So the surface charge density divided by epsilon naught inside, away from the edges. You know, there's a lot of time where we're going to say, like, you know, ignoring parts, you know, we're going to deal with the parts and ignore the parts that aren't helpful to us or are complex. And honestly, that's a lot of science, working out what we can ignore. So this charge per area is, you know, this is the surface charge density, which is the total charge Q divided by the cross-sectional area of a plate. And I can combine these together to say that, okay, the magnitude of the change in electric potential between the two plates is equal to the electric field, the total charge, over epsilon naught times A times D, the separation between the plates. And the reason why that's useful is because I can say, okay, the change in electric potential is equal to the charge stored on the plates times the distance between the plates times epsilon naught times the area A, or Q is equal to the constant epsilon times the cross-sectional area A divided by the separation between them, times the change in electric potential between the two plates. Now, this is cool because this section right here depends only on the geometry of the system. You know what this number is at the factory. And so I can take this number and define it as the capacitance C in units of farads, where the farad is named after the scientist Michael Faraday. We're going to talk about him in much greater depth when we get to magnetic fields as well. And I'll direct you to an episode if you have any ability there's a variety of places to see the more recent series of Cosmos. There's one episode of Cosmos, if you have any sort of streaming service, that has a very good biography of Faraday, and I will direct you to that when we get to magnetism. Now, the 1 farad is 1 coulomb per volt, and that's quite a large number. We'll be working with capacitances typically in microfarads or nanofarads. You know, if I have all right, let's just take one quick sample to show you where this comes from. Suppose that I have, let's see, a cross separation of 1/10 of a millimeter. Very tiny separation. And actually, you look at the end of this chapter where we talk about, like, typically there's like a little thin layer of something holding those two plates apart, a dielectric. We're just going to deal with space for right now. The dielectric doesn't add a tremendous amount of complications, but it makes it a little bit more complicated, perhaps to no great use, especially in our first pass through. Now, if I've got, let's say a capacitor, you know, if we're trying to get, let's try and get like a real capacitor. So if it's, say, call it 1 centimeter across, or about 1.5 centimeters across, then the cross-sectional area is the radius squared times pi, or an area of 1.77 times 10 to the minus 4th square meters. Now, epsilon naught is 8.85 times 10 to the negative 12th. So epsilon naught minus 12, let's see, Coulomb squared per Newton meter squared. So the capacitance of this will be epsilon naught times the cross-sectional area divided by 0.0001, or, well, that would just give us a capacitance of 1.56 times 10 to the minus 11th farads, or 15.6 picofarads. That's why if you look in a lab, 1 farad or even a substantial chunk of a farad capacitor is going to be pretty darn sizable.